recording. And remind me to stop recording when I finish. Okay, so it's recording whatever you're seeing here. You're going to be recorded. This is so. What kind of math do you need to know for this? You don't need to know very advanced math, but you need to know like 9th grade math. Basically, I'm going to sort of go over a couple of things here. You need to understand how the metric system works. That we didn't mention the metric system, but we're going to. How scientific notation works. Yes, we mentioned that already, which enables us to write very large and very small numbers. Not only write them, but multiply and divide them. A little bit of simple algebra, basically things you learned in 8th grade, maybe a little bit in 9th grade. We use symbols like ax equals b to solve this for various unknowns. And we work a little bit with units. When you use an equation, each number has units associated with it, therefore the answer will have units. And we're going to answer everything today. So here's a picture of a pole vaulter. It's a very big fella, he's 7 feet 6 inches. And basically, I said 7 feet 6 inches, but why 7 feet 6 inches? Well, he could be 2.29 meters tall. This is the same as 7 feet 6 inches. In Europe, everybody uses the metric system. In this country, we still stick to what's called the English system here to measure distances and other things, like weight, for example. Again, in Europe, you would say he's 141 kilograms, and here we'll say, well, he's 310 pounds. So basically, every number has a unit associated with it, not just a number, but a unit associated with it. And again, English units that we use here are inches, feet, pounds, ounces, gallons, miles. But if you look at a soda can, you will see 2 units. This soda has 355 milliliters. The ml is called a prefix, or in the English system, this would be 12 fluid ounces. So the metric system is in liters, and in the metric system, we also have prefixes. In this case, the prefix is milliliter. And this is all based on multiples of 10. We're going to see that in the meter. So the basic unit for measuring distance is called a meter in the metric system. Not a foot, not an inch, but a meter. A meter is pretty close to a yard. You can see a yard here. So a yard is a little smaller than a meter, but they're pretty close together. And as I mentioned before, the metric system is prefixes. So here are some of the prefixes you may be familiar with. Kilo, like a kilometer, means 1,000. The word centi means 1/100. The word milli means 1/1,000,000. So if you want to weigh something, let's say a penny, you put it on the scale over here, and you read the scale, and the scale will tell you the weight of the penny in grams, which is the unit that you use for weight. Now, right now, we're not going to do graphing. Toward the end of the semester, we're going to need a little bit graphing, but right now, I'm going to skip this. But let's talk again about the metric system. The metric system works like our base 10 place value number system. What does that mean, all that? Well, if you have a number like 6357, the position of these digits tells you its value. For example, the 7 here, what does that tell you? It tells you how many ones. The 5 here tells you how many tens. The 3 here tells you how many hundreds. The 6 here tells you how many thousands. Now, 1,000 is 10 cubed. 100 is 10 squared. 10 is 10 to the 0, 10 to the 1. And 10 to the 0 is 1. Any number raised to the 0 power is 1. So we say this is a place value number system. Well, the metric system has words for these. You're probably familiar with kilo. Kilo means 1,000. So you have kilograms, that means that's 1,000 grams. These you probably never heard of, but they're there. A hecto means 100. So hectometer would be like 100 meters. Deca means 10. And also going the other way, we'll see, if you get small numbers, we'll get to the small numbers a little bit later. So if we went to, well, again, so we get to that a little bit later. So scientific notation, which you mentioned before, numbers can be written what's called standard form of scientific notation, which has a lot of zeros. So scientists have come up, as you saw before, with a way of writing very large and also very small numbers in scientific notation. And we use powers of 10. Keep in mind that 10 is 10 to the 1 power, 100 is 10 squared, 1,000 is 10 cubed, 10,000 is 10 to the 4. The number of zeros tell you what power of 10 is. 4 zeros means it's 10 to the 4th. And if you were to write these numbers, you would write it as 1 followed by 6 zeros. 10 to the 6 would be 6 zeros. 1 followed by 2 zeros. You can see it over here. Six zeros up here, 2 zeros here, and 1 followed by no zeros. Here it is. 1 followed by no zeros. So in scientific notation, let's say you have a number like 6,500. We can write this as 6.5 times 1,000. You multiply 1,000 by this, you get 6,500. But 1,000 is 10 cubed. So we replace this by 10 cubed. Now, it's not a big difference writing this or this, but if you got more zeros here, a bigger number, it does make a difference. So let's say you did something like this. This is 7.4 billion, and it would be 7.4 times 10 to 1 billion. And 1 billion is 10 to the 9. You count the number of zeros, 9 zeros, 10 to the 9. A lot shorter way than writing this number over here. So the standard form of scientific notation is this. You got a big number, you write it this way. This is 10 raised to some power. The power is called the coefficient. And multiply by a number that this number is bigger than 1, but less than 10. Okay, so it's got to be bigger than 1, but less than 10. That's how you write it. You move the decimal point until you get that. And we're going to show you. For example, this number is really this number here in the bottom, expressed in scientific notation, the same number as that. How do you figure out how to write it? Okay, so that's the next part. Let's say we want to express 870,000 in scientific notation. Here's the steps to do it. Number 1, write the number without commas. Here it is, without commas, without that comma. Number 2, place a decimal point so that the first number will be less than 10 but greater than 1. In other words, where would you put a decimal point to get a number that's less than 10 but bigger than 1? Aha, right over here. Right over there. Okay? Count how many places you had to move the decimal point. How many? The decimal point originally was here. And we moved it 1, 2, 3, 4, 5 places. 5 places. And therefore, this number now is 8.7 times 10 to the 5th. So that's how you write a big number in scientific notation. Now, some of you, I'm sure some of you studied this in the past. You may have forgotten it, or maybe not. But now let's go to what I sort of threatened to do. Let's go to small numbers. Small numbers. First of all, we've covered large numbers. But you notice that as we go from here to here to here, each number is 1/10 of the previous one. 1/10, 100 is 1/10 of 1,000. 10 is 1/10 of 100. 1 is 1/10 of 10. Let's keep going. Why stop here? This is 10 cubed, 10 squared, 10 to the 1, 10 to the 0. If we take 1/10 of that, let's just keep going, and we get, first of all, a marker that we're going to numbers less than 1, called the decimal point. And this is 1/10 of 1 is 1/10. We write it this way, 0.1. And since we're going 3, 2, 1, 0, let's keep going. What comes back after 0? -1. And then the next one will be -2. There'll be 1/100, because this is 1/10 of that. And the next one will be -3, etc., etc., etc. And each of these has a name, prefix associated with it. So 1/10 of something is called a deci, 100 something is called a centi, 1,000 of something is called a milli. So negative numbers mean, negative exponents mean this is a small number. And again, the way to remember, 10 to the minus 1, which is 0.1, is 1/10. 10 to the minus 2 is 0.01 or 1/100. 10 to the minus 3 is 0.0001 or 1/100. Remember that 10 squared means 1 followed by 2 zeros. So 10 to the negative 2 means 1 preceded by 2 zeros, but you have to count the 0 to the left of the decimal point. In other words, you have to count this 0 here. So 0.02 has 2 zeros in front of it, so we'd write it as 10 to the minus, sorry, 0.001 has 2 zeros in front of it, and you will write the number as 10 to the minus 2. Any number can be represented as some integer times 10 raised to some power, and that power could be now positive or negative. So 30,000 can be written this way, 0.0003 can be written this way. Now, we covered this sort of just now. We talked about numbers in this range from kilo to milli, but we could have kept going, except there are no names except every third one. So if we get to 10 to the minus 6th, which is 1/1,000,000th of something, this has a prefix of micro, and the abbreviation is mu. So mu m means a micrometer. And what's a micrometer? It's a millionth of a meter. So I have something is 5 micrometers thick. It means it's 5/1,000,000th of a meter. Nano is 10 to the minus 9th. This is a 9 here. 10 to the minus 12. And going this way also, mega is 10 to the 6th. Giga is 10 to the 7th. Tera is 10 to the 12th. So these are all the units. You've probably heard some of these, not in conjunction with meters, but with other things. We're going to get into that in a second. But here's some examples of very big and very small numbers. The mass of the whole solar system is this number here. You going to write that? I don't think so. This is the way you're going to write it. 3 times 10 is 53 zeros, so it'll be 3 times 10 to the 53rd power. Okay, I'm going to skip that. So again, let's see if we can do a couple of problems. Which is the correct coefficient of 147,000 when it's written in scientific notation? Coefficient meaning the whole number, and you multiply by 10 to something. So okay, so basically what that means is that the first number has to be bigger than 1, less than 10. So you got to put the decimal point right over here. So it'll be 1.47. Okay, so most of you see had the right answer, 1.47. And of course, to write it, if you want to write the whole number, 10 to the, well, how many? 1, 2, 3, 4, 5. 10, it will be 10 to the 5th, because I had to move the decimal point 5 places to get it here. So which of the following is the correct way of writing 245,000 in scientific notation? Don't forget, you got to move the decimal point from here all the way down to here. How many places is that? Well, 1, 2, 3, 4, 5, 6, 7, 8. 7, 8. 8 places. So a few of you got that wrong. That's okay. It's all right. That's what we're doing. Okay. Let's do the same thing with very small numbers, 0.0043. So how would you change that? First of all, we're gonna first write the number without the decimal. Okay. Second, actually I should close this. Second, place the decimal so that the first number is 1 or more, but less than 10. So where are you going to put the decimal point here? Well, you're going to put it right over here. And we can see that right over there. And then to figure out what is the power here, well, how many places do you have to move the decimal point to get it there? And you can see you had to move it 3 places from where it was originally. And therefore, this will be 3, but 10 to the minus 3. Because this is a small number. You're moving the decimal point to the right, making it smaller and smaller. So let's write this particular number for a little practice. Again, write the number without the comma. Here it is, without the comma. It's not the comma, without the decimal point. Place the decimal point so the number is between 1 and 10, and that's over there. Count how many places you had to move, 6 places. And lo and behold, you have 8.32 times 10 to the minus 6. Okay, so this is like before. I'm going to skip a couple here. Okay, this is all the same thing that we've done, so I'm not going to do it again. But I'd like to spend a little time on this. So now you got numbers in scientific notation. You're going to multiply them and then divide them. So how do you do that? Well, multiplying with scientific notation requires a couple of steps. You multiply the coefficients, in other words, the numbers like 1.58 or whatever, and then you multiply the powers of 10. And then you combine the results and then you put it in proper form. So let's do an example, or we're going to do an example in a bit. But right now, let's talk about the metric system. So, as we mentioned before, the metric system is based on these tens that we've been doing. So let's talk about using the metric system to measure distance. So the meter is this particular unit that we use to measure distances. That's the base unit, 1 meter. The meter is about a yard, and you can see here a ruler with a meter. But sometimes you want to measure things, you want smaller numbers. Meter is not good. You want something smaller. So what do? You divide that meter into 10 equal parts, like I did here. So this is 1 decimeter, 2 decimeters, 3, 4, 5, 6, 7, 8, 9, 10. 10 decimeters. And you can use a decimeter, though those are rarely used. But if you take a decimeter, let's say the distance between here and here, and you divide that up into 10 equal parts, which is done here, you get something that looks like this. You have 10 equal parts over here between 46 and 47. So each of these little distances is 1, well, counted. Here they are. There's 10 here, 10 here, 10 here, 10 here, 10 here, 10 here. 10 times 10 is how much? Is 1,000. I'm sorry, 10 times 100 is 1,000, because these centimeters, there's 100 of them here. So each of these, this little distance is 1,000th of a meter. Here you see another picture of 1,000th of a meter next to a real ruler. So each of those has a name. 1/10 of a meter that we saw before is called a decimeter. 1/100, these lines over here, right, are called centimeters. And these tiny things that you don't see them here because they're so tiny is called millimeters, and there's a 1,000 of them here. So basically 1/1000 is a milli. Now, if you want to change from one unit to the other, all you got to do is move the decimal point. But in order to do that, you got to remember these names. Kilo, hecto, deca, deci, centi, milli. So there's a way to sort of help you remember them, pseudonym. and that's called King Henry Died Drinking Chocolate Milk. King Henry Died Drinking Chocolate Milk. And these could be used, no, not for meter. This could be used for anything. For a gram, I can put gram here. And kilo, I have a kilogram, the hectogram, decagram, decigram, centigram, milligram. Did you take your vitamins today? You took a certain number of milligrams here. Another unit that, well, we'll get to the other units in a bit. We could keep going, as I mentioned before. Milli is 1 million, is 1/1000, but we keep going, you get 1/1,000,000th, 1/1,000,000,000th. 1/1,000,000th is called a micro. 1/1,000,000,000th is called a nano. Going the other way, we can also take every third decimal place, we give it a name. So going three powers of 10 over, you get a million. It's called a mega. A billion is called a giga. And of course, we keep going to a trillion, that would be a tera. And any of these could be used with the same prefixes. For example, you probably heard this, something like kilobytes, or something like this, hertz, megahertz, gigahertz, terahertz. And these, of course, are associated with computers.
Call from.
Yeah, now I unplugged the phone. All right. So all these prefixes are used in modern life, and you've been using them, probably didn't know they were part of the metric system. Okay, so again, we have here the whole thing from tera, giga, mega, kilo, and then the ones here that go hecto, deca, deci, cent, and the unit here could be any one of these. And same thing here, we have milli when you get small numbers, micro, nano, pico, 1/1,000,000th is pico. Let's see, I think. And again, to remember, at least for the ones over here, from here to here, you can easily remember them, because if you remember, King Henry died drinking chocolate milk. This tells you how many places to move. For example, let's do an example. Supposing you measure something, somebody tells you 125 millimeters, and how many meters is that? Wait a minute, how do you do this? Well, very simply, 125 millimeters. Millimeter is, over here. Meter is over here. To go from here to here, I got to go 1, 2, 3 places to the left. So I'm going to go 1, 2, 3 places to the left. Put the decimal here. I could put a 0 here. And so the number that I put here is 0, 0, 0.125. To go from kilometers to centimeters, or kilometers over here, you're going to move the decimal place 1, 2, 3, 4, 5. So start here. As you move the numbers around, and I'm going to type this in. Okay, you got 3, 4, 1, 2, 3, 4, 5. That's how many. 3.5 kilometers is that many centimeters. Same thing with going from decimeters. So here you see the numbers. So this sort of summarizes all the metric prefixes that are small, centi, and there's 3 more here that aren't used very much. So I'm just using every third one: milli, micro, nano, pico. And the large ones are kilo, and then mega, giga, tera. And you can keep going past that, peta. Now you may ask, how did the meter come by? Who Who died and made somebody king who decided what the meter is? I don't know. But this is the way it was defined originally in 1791. If you go from the equator to the North Pole through a line going through Paris, 1 meter was defined originally this way. It's 10 millionth, 1 millionth of the distance between the equator and the North Pole. And basically that's how you get this distance. It's about as big as a yard. But originally it was defined that way. Then it was redefined 1889. There was, first of all, a prototype of a meter, and there was a original meter stick in a museum. It was in a cage. It was enclosed in glass. But in 1960, it was redefined as 1.65, 1,650,703.70 wavelengths of light emitted by an atom called krypton 86. Now, krypton is the stuff that makes Superman weak. It's a fairly complex atom. But now, in 1983, it was redefined, and this is what it is now. A meter is the distance light travels in a vacuum in this amount of time. So that's how we got that meter stick. For example, if you want to measure something like this, they want to measure, this is a table. Here's a meter stick. Use whatever unit you like. Probably, how would you measure how wide this is? Well, probably you would use centimeters. So the length of the stick here is how many centimeters, approximately? Again, you can answer these questions. Let's see how you guys are doing. Just look at the ruler. How many? Don't forget, these lines are centimeters. This is a meter stick we're looking at down here. Yeah, so these are 32 centimeters approximately, okay? Approximately 32 centimeters. And again, if you wanted to change that different unit, that's the next question, I think. No, it's not the next question. But let's do it anyway. If we wanted to change that to a different unit, say we wanted to change it to, you got to remember this. Okay, King Henry. So right now we're in centimeters. So you want to change it to kilometers. 32 centimeters. We want to change that to, well, first of all, how many meters is that? Again, which one of these would be the right answer in meters? And to going from centimeters to meters, this is, we'll tell you what to do. I don't hear any thinking. So we have 32 centimeters, right? And how many meters is that? 1, 2. So the decimal point is here, 32. And now you guys are answering. All right, good. Yeah, so it's 0.32. Okay. How many kilometers is that? Well, you just got to now keep going. You got 1, 2, 3, 4, 5. So you got to keep going. I'm not going to do it here, but obviously it's going to be this number over here, right? Because it's going to be, this is the only tiny number. So that distance is a very small number. Obviously, kilometers like a mile. How long is this in miles? Well, I don't know, but it's very small. Not a lot of miles, right? And millimeters. Oh, you go the other way now. For millimeters, you started off with 32 centimeters up to here. And millimeters, you go the other way, it'd be 320 millimeters. Okay, so let's look at multiplying numbers in scientific notation. So let's say we have two numbers, both in scientific notation. How do you multiply? First of all, multiply the coefficients. Coefficients being this number, multiply by that number. Use your calculator or whatever way you want to. So 6 times 2.5 is 15. Multiply powers of 10. Well, you know, this is 10 times 10 times 10 times 10. 4 tenths, that's what that means. Here, this is just 2 tenths. So the moral of the story is, how many tens you got now? Well, you got 4 here and you got 2 here. You got 6 tenths. So when you multiply, you add the powers, the exponents, because of this reason. So 10 to the 4th times 10 squared is not 10 to the 8th. You don't multiply these numbers, you add these numbers. And this is why you add them. And so you got 15 times 10 to the 6th. This is a good answer. This is the right answer, but it's not in standard form of scientific notation. We need this number to be between 1 and 10. So we're going to move the decimal point one place here, making it smaller. It means we're going to make this bigger by a factor of 10, 10 to the 7th. All right, let's try a little problem. This one here, let's see if you can try it. Don't forget, you're going to add the powers of 10. One of them is a negative number. So we know 8 is going to be that number, 2 times 4, so all of these are incorrect. It's going to be either this or this. And of course, it is this because you got to add the exponents. 7 minus plus or minus 4 is equal to 10 cubed. Okay. So let's talk about dividing numbers in scientific notation. Dividing with scientific notation, just like multiplying. You divide the two coefficients and you divide the powers of 10 and combine these results. The thing to remember is, let's say you have a number like this. So you're going to divide 5.4 divided by 9. So you get out your calculator, whatever it is. But 10.6 means 10 times 10 times 10 times 10. It's 4, 5, 6. And you're dividing it by 10 squared, which is 2 tenths. Now what happens here, I'll do a different color, is this 10 calculates, cancels this 10, and this 10 calculates, cancels this 10, and so you're left with 4 tenths. So this will be 10 to the 4th, means when dividing, you subtract the exponents. So again, 5.4 divided by 9 is 0.6. 10 to the 6th divided by 10 squared is 10 to the 4th. Subtract the exponents, and you write the number is 0.6 times 10 to the 4th. Now, this number is mathematically correct. It's just not in standard form. I got to move the decimal point one more place. As I move it that one place, I make it bigger by a factor of 10. So that means I got to make this one smaller by a factor of 10 to have the same number. And you get that. So again, one more example here. You can watch this in the video if this is too fast for you. I don't think so. 4.4 divided by 1.1. 10 to the 6 divided by, so this one's a little tricky. 10 to the 6 divided by 10 to the minus 3. So what's the power of 10? Well, it's the top, which is 6, minus the bottom, but it's minus a minus 3. And you know from 8th grade that minus a minus becomes plus. So basically it's going to be 10 to the 9th, as we see here. And this is already in proper form, so you have no further work here. Let's do a couple of examples. All right, so let's see if you can do this. So this divided by that, we know is 8, well, 0.8. So what's the power of 10, though? But this, okay, so that's the answer, but it's not in standard form, but the choice here doesn't give you the standard form. Yes, it does, okay. But so this is correct, but this one here is also correct. If you make this bigger by 1, make it smaller by a factor of 10, yes, so this would be also the same answer. Okay, so I'm not going to do this one here, but you can see that 1.9 times 10 to the minus 2 minus a minus 4. Okay, and you figure the rest yourself. Okay, I'm not going to do this. Let's talk a little bit about using units in science. So we're usually we would end my first period by now, but I don't have a whole lot more to go. We're just going to keep going so we can finish early. Normally, right now, we would stop and do the lab, but the lab is just problems. In this case, just problems with this. And I want to show you that in a bit. But using units in science, that's what we still have to do that. And one other thing, just a little bit of algebra. So 5 centimeters times 5 centimeters is what? Well, 5 times 2 is 10, but 10 what? Well, centimeters times centimeters is square centimeters. So when you multiply by this, the answer is 10 square centimeters. But what's a square centimeter? Well, you see it on the right here. It's a squares that are a centimeter on each side. And it's 10 of them. That's the answer. This is the answer, basically. You write it this way, but you would to draw it that way. How about this one here? 10 centimeters cubed divided by 10 centimeters. I'm sure you already know what to do that. So 10 centimeters cubed is what? Centimeters times centimeters times centimeters divided by 5 centimeters. One of these centimeters will cancel off, and you will have 2 square centimeters. All right, this has been pretty easy, right? So let's start a little harder one. Let's try that. So this basket here has pears and oranges in it. There are 6 pears and 2 oranges. If I take the number of pears and divide it by the number of oranges, what do I get? Do I get 3 grapes? No. Strawberries? No. What do I get? Well, this is what I get. It's 3 pears per orange. You write it this way. But what it means is that for every orange, there are 3 pears. So for this orange, there are 3 pears. And for this orange, there are 3 or more pears. The ratio of pears to oranges is 3 to 1, basically. That's what that means. So we usually write it this way: 3 pears per orange we write it this way, but this is what it means. It's a ratio. So of course this happens very often. One of the things we'll be doing is measuring the velocity of things, how fast are they moving. So let's just look, let's say this is a toy car or a car moving 10 meters in 2 seconds. Its speed is distance divided by time. 10 meters divided by 2 seconds, how much is that? 10 meters divided by 2 seconds is 5 meters per second. Just like pears per orange, we have meters per second. Okay, so I'm going to skip a couple of things here and go to some simple algebra. So basically, the algebra is pretty simple. It's of the form, for example, 3 types. Given a number like this, you could be asked to solve this for A, B, or A is already solved for B and C. Okay. Or given a number like this, solve it for X. Or given a number like this, solve it for X. Okay. You have to remember the equal sign here means that whatever is on the left side is the same as whatever is on the right. It's like a balance. You're balanced right now. When you have an equal sign, the equal sign says you have 3 plus 9 here, and you have 12 here, and you're balanced because they're the same. So whatever you do to one side, you got to do exactly the same thing to the other side. That's the thing to remember. That's what an equal sign says. So, for example, if you want to solve this for B, which is the easiest one, that means you want to isolate B on one side. You want B by itself. So what do you got to do to the right side? You multiply by C. And if you do that, you're going to multiply this side by C. And these C's cancel off. So what do you get? You get B is equal to AC or CA. So the same thing was in the distance divided by time. You can solve for distance. Distance would equal speed times time. This is almost identical to what we just did. All right, so coming back to this, if A equals B over C, what if you want to solve for C now? What would C equal? Well, I'll give you a little hint. In the previous problem, we found B is equal to that. Now can you solve for C? Whatever you do to one side, you got to do the same to the other side. To isolate the C, I have to divide this by A. I have to divide that by A also. The A's cancel here. And so you have C is equal to B over A. How about equations of this form? How do you solve this for T? Well, it means you have to isolate T. So what do you got to do? Well, you divide both sides by 5. So 5's cancel here. You have just T squared. And 125 divided by 5 is 25. So is that the answer is T25? No, because they're asking for T, not T squared. So whatever you do to one side, do to the other. If you want to get T here, you take the square root of T squared, and then you got to take the square root of 25. So T is equal to 5. Okay, I'd like to go back to something I skipped here because you may need it for the answer some of the questions. So coming back to working with units, you purchase 10 gallons of gas and you pay $30. So this goes back to what we were doing with the pears and oranges. So basically what that means is that 10 gallons is the same as $30 because you bought 10 gallons. So 10 gallons equals $30. So the question I have for you, 2 questions. How many dollars did you pay for a gallon? Would you pay for a gallon of gasoline? You bought 10 gallons, but how much, if you only bought 1 gallon, what would you pay for it? The other question is, how many gallons can you get for $1? So I only have $1. Give me $1's worth. How many gallons will he give you? So let's do these questions one at a time. First of all, if I take 10 gallons divided by $30, what do I get? Well, 10 divided by 30 is 0.3, right? But what are the units for this? Same as pears and oranges, gallons per dollar. So 30 gallons per dollar, 0.3 gallons per dollar. So for $1, you can get 1/3 of a gallon approximately. Okay, that answers this question. How many gallons can you get for $1? How do you answer this question? Well, do the opposite. $30 divided by 30 gallons, or 30 divided by 10 is 3. But what do you got here? 3 what? Well, you got dollars on top and gallons on the bottom. Okay, so what I'm going to do right now is stop recording. So everything I did on math here will be recorded